Hi, I'm Mariah Salazar. Welcome to the fourth webinar in our Arc Hydro in Action webinar series, Arc Hydro, Support for Hydrologic and Hydraulic Modeling. This webinar is being recorded, and the recording will be posted on the webinar registration page and available for on-demand viewing. You will receive a follow-up email that includes a link to this page. It can take several days for the recording to be published, so you can expect it to be available next week. This webinar includes several polling questions. Please participate in the polls. We appreciate your responses. We have included QR codes within the presentation. You should be able to scan these codes with your mobile phone and access resources. If you aren't sure how to use QR codes, don't worry, I will be sharing links in the chat dialog box. I encourage you to post questions in the questions dialog box during the webinar. We will answer as many questions as time allows. At the end of the webinar, a survey will launch. This is a short survey and will only take a minute. Please complete the survey. There are only a few questions. If you missed the first 3 webinars or would like to watch them again, a link for on-demand viewing can be found on the webinar series registration page. One last announcement before we get started. I'd like to highlight the Applied Meteorology using ArcGIS webinar series. This might be of interest to you since there is no hydrology without weather. Let's get started with the polling question. All right, everyone should be seeing a poll. Did you attend or watch any of the first 3 webinars? Maybe you attended Arc Hydro and ArcGIS Pro, maybe Flooding and Forecasting, or Hydrology and Hillslope. Or maybe you're new to the series. We have quite a few responses coming in. I'm going to give it a couple more seconds. It looks like, Dan, we have quite a few people new to the series today.
Okay.
And it even spread between the 3 previous webinars. Oh, looks like Arc Hydro and ArcGIS Pro is in the lead now. Give it a couple more seconds. Thank you for your responses. I'm going to go ahead and close out this poll. And we'll share the results. So here's our results, Dan. It looks like the most popular webinar was Arc Hydro and ArcGIS Pro. And we have quite a few new people today. So let's get started. Today, Dan is joined by Pete Sinkhofen and Warren McKenney from Streamline Technologies. Pete Sinkhofen is the president, founder, and owner of Streamline Technologies, Inc., and the original developer of ICPR. He has been a water resources professional for more than 40 years, specializing in distributive, physically based integrated modeling of large-scale surface and groundwater systems. Warren McKenney is a senior water resources engineer at Streamline Technologies. He has been in the water resources field for 18 years and has extensive knowledge utilizing GIS applications for asset management as well as H&H model development. Dan, I'll pass it to you.
Well, thank you. So quick wave, and I'll turn my camera off while I'm presenting, and then we'll come back afterwards for Q&A. So in this webinar, we'll do a quick review of the series, and we'll spend a few minutes talking about Arc Hydro for groundwater. We'll introduce the principles of model integration, then we'll examine several existing H&H model interfaces, how they were built, and pros and cons of each. We'll sum it up, and we should have a few minutes for questions. So today we'll look at the whole aspect of our GIS hydro modeling cycle. And I tried to make these arrows as messy as possible. Really, everything goes here. The specific model integration use cases we'll discuss include stream stats that we talked about last time, culvert calculator example that extends hydrologic modeling into engineering design, modflow integration is an example of how I integrate groundwater models. Then we'll talk about surface hydrology and hydraulics through HC, HMS, and RAS, and finally look at fully integrated H&H modeling through ICPR that Pete and Warren will cover. So let's revisit some of the key points from this webinar series so far. We'll start with what is Arc Hydro. we said that the idea behind ArcHydro is to provide GIS framework for development of integrated analytical systems for water resources. It includes the data model, tools, workflows on how to best use the tools for particular use cases, and the community of users with common interests and patterns of use. Note that data is not part of this. ArcHydro is not a specific data set. It is designed to work with many data that you load into the ArcHydro data model. In ArcHydro, we have many tools and workflows in many different areas of water resources. There are over 200 tools. You will most likely never use all of them, probably 30 to 40 tools that are specific to your needs. There were a number of questions over the last few weeks regarding the ArcHydro for groundwater, so let's cover that in some detail. The project launched in 2004, 2 years after the initial ArcHydro was released. David engaged Dr. Norm Jones, a professor at BYU, to help him with the groundwater and subsurface domain expertise, and had Gil do his PhD on the subject. ArcHydro for groundwater, like the surface component, includes the data model and a set of tools. In 2007, Acquaveo took on development of the groundwater tools, and they were released in 2009. And the ArcHydro groundwater book was published in 2011 by Esri Press. Tools are organized in 3 extensions. First one is Groundwater Analyst that lets you manage well and time series data and transition between point and surface information representation. The second extension is the Subsurface Analyst that focuses on borehole management and allows you to, among other things, construct 2D and 3D subsurface representation from borehole data. These structures can then be used to support other groundwater and subsurface analysis. And the final extension is the ModFlow Analyst that focuses on ArcGIS integration with ModFlow groundwater model. And while it focuses on ModFlow integration, the same infrastructure can be used to support other groundwater models. Groundwater Analyst is free, while Subsurface and ModFlow Analysts have a fee associated with them. Acquaveo also provides training related to the ArcHydro groundwater, and all that information is available at Acquaveo's website. During the last 3 webinars, we started an important modeling discussion. Basically, we said that models are not truth, they are approximation. We are still going to use them and will not wait for perfection, as it will never come. And lastly, it is your responsibility to understand the tools and models you are using and to interpret the results you are getting. So, are the data, models, and results good enough for what you are trying to accomplish? And if not, you need to change them. This also covers the data. This will be even more relevant for today's discussion as we are discussing general model integration and use. Let's define some basic principles of GIS and model integration. We'll talk about types of model integration and key elements in building these interfaces. And while we'll focus on our H&H models, these principles apply to all external models and their integration with the GIS environment. When building an interface, there are a number of key elements that you need to consider. How the data will be moved between GIS and the model, what the user interface will look like, how is the control path between the 2 components, and what software and hardware infrastructure is there to support the integration. Based on all these factors and ultimately how the user will develop and run the system, the interface can take many shapes. So let's look at some types of model integration. The simplest model integration, it's really not integration, is basic GIS processing of data that eventually end up in our model. It covers operations like delineating watersheds, calculating areas, or curve numbers. There is little actual integration here, just data processing. The next type is linked or loosely coupled approach. Here, GIS and model are managed independently with their own interfaces, and integration is achieved by sharing data. In more advanced implementations, applications can control execution of each other in a more integrated way. In integrated or tightly coupled system, the two systems have a unified front end and control, although behind the scenes there are two separate modeling systems. And finally, in the embedded system, the engineering model is built into the core GIS capabilities. For example, the spatial analyst porous path function implements subsurface dispersion model as native GIS function. When building or using an interface, you really have to consider many factors. It is hard to say which of these factors are the most important for you. That will really depend on particular situation, and even within the same organization, it might vary from project to project. As a developer who has built many of these interfaces over the years, my biggest concern is the longevity of the interface. How difficult will it be to maintain the interface as both GIS and model capabilities change, often at different paces? Who will maintain this interface as the capabilities advance? Now, general model integration is not something new. There have been systems and frameworks out there whose purpose was to facilitate easy integration of various models and techniques, and you might have run into some of them. Within Esri universe, you can use Model Builder and Geoprocessing framework for model integration. Now, let's not forget data interoperability extension, or FME, when you have to do some heavy data integration lifting. So what should be your approach when looking at implementing or developing an integrated system? That will really depend on your particular situation and is often driven not by technology, but rather by institutional requirements. Do you have to use a specific model? Does your county, for example, dictate how you're going to do specific modeling? Do you need to use it just once or over an extended period of time? So is it just design or is it operational mode? Do you need to have access to every possible configuration tweak in the model? If so, you cannot hide the user interface. If you develop your own integrated model and somebody does not like your results, will you get sued? And many other factors. But almost always it is if there is an existing product that provides an interface between your GIS and the model of choice, you're better off getting it than developing your own. Today, using Python and ArcPy, it really provides an incredibly powerful integration platform for all kinds of model integrations. We'll now look at several systems. We'll start with StreamStats that we talked about in the last webinar. The model is a statistical hydrologic model based on regression relating basin characteristics to flow. So this is an example of tight coupling where GIS and model communicate through data derived in GIS and passed to the numerical engine as a service call. The application interface hides both systems and provides a unified and streamlined end user interface. It hides the complexity of both systems and makes the integrated application easy for anyone to use. But it's a black box system that does not allow you to modify almost anything. The next example is the Prince Edward Island culvert calculator. This is a project we did together with Esri Canada for the government of Prince Edward Island. It's a web app that lets you click anywhere within their domain of interest, and within minutes it calculates the 100-year discharge and sizes culvert based on that flow and different material types. The hydrology is based on rational method and uses climate change adjusted precipitation intensity duration curves. And the culvert design is based on their standard road design handbook. All that is wrapped in a single Python script working on top of ArcHydro pre-processed terrain data. The script is published as a geoprocessing service and front-end interface is built using Web App Builder. So let me show you how it works. It's a Web App Builder application, and you start at the full extent of the province. You zoom in at the general area of interest until you can see enough detail to place your point of interest. You open the GP tool pointing to the culvert calculator service. Place the point where you want the culvert designed for example, at this point at the intersection of the stream and the road, and run the tool. And in about a minute, the watershed is delineated, characteristics are extracted, hydrology computed, and finally culvert is designed. And one-page report, a PDF, is generated with watershed and hydrology details and possible culvert types that can be placed at the location. What is really neat about this app is that construction crew in the field can run that tool on the spot on their phone, and based on what pipe they have on their truck, build the culvert right there and then. No need to go back to the office, get the design done, and then go in the field again. So this is an example of embedded system where the model is fully implemented within GIS. The application interface provides a streamlined end-user interface and makes the application easy to use for anyone. But it is a black box system that does not allow you to modify anything. But some alternatives are built into the analysis, so there might be less need to tweak anything. Now a bit of change of pace, and we'll discuss some of the groundwater model integration issues. We'll talk about a project that Aquaveo developed for Virginia Department of Environmental Quality and deals with well permitting. The key idea is to use an existing mouthflow model as a baseline model that represents current conditions. As new wells are proposed, they are inserted into the model is run, results brought back into GIS, and are evaluated against development regulations. And based on that comparison, validity of the well location and pumping pattern is established. Here's what that workflow looks in a model builder that automates the process. You add a well in the ModFlow well record. You export to ModFlow well data structure. You run ModFlow with updated wells, and finally get ModFlow results back into GIS data structures. So in more detail, here is how to create a new feature in the well feature class using data associated with candidate well coordinates, with coordinates, pumping rate, and screen elevations. Note that each time you add a well, we assign a unique Hydro ID to it, so it's using all the core ArcHydro data development principles. Then we create a ModFlow instance based on the location of the well and the screen elevations, including finding appropriate ModFlow cells that this proposed well fits into. And again, notice the use of the Hydro ID to relate the well information to rest of the information in the data model. These data are then exported into ModFlow well text file. And the next step is to run ModFlow simulation with candidate wells as input. And the resulting drawdown file is exported as part of the solution. Finally, once the simulation is completed and results generated, they are imported back into GIS for comparison with the baseline simulation. And generate the appropriate data structure and guide well approval rejection. There can be a number of different criteria for comparison, looking at change in flows, observed versus simulated equivalents, or drawdowns at key locations, or a whole drawdown map, or capture zones. And finally, you can generate the report artifacts. This is an example of tight coupling where GIS and model communicate through data derived in GIS. GIS also controls the execution of the numerical model and provides the single interface for execution of the whole workflow, both for pre and post processing. In practice, this is done by GIS specialists at Aquaveo that execute this process on as needed basis based on Virginia DEQ requests. This concludes our groundwater and ModFlow discussion. In the second webinar in the series, we talked how there are different methods within GIS context to define the floodplain. And we focused on simple methods that use only topographic and optionally observed data to define flood extents. You also told us that you do use more advanced techniques for flood delineation, so we'll now look at more complex methods based on hydrologic and hydraulic modeling. We got a number of questions regarding support for HECs, HMS, and RAS, so let me cover that in some detail. HEC GeoHMS and HEC GeoRAS are ArcMap-based companions to HMS and RAS. These are HEC's products that were developed by my team for HEC and are not part of ArcHydro but separate entities. Development of them stopped with release of ArcMap 10.2 and thereabout. Since then, my team has maintained them, and you can download the latest ArcMap versions from our Water FTP site. And there are currently no plans to move them into Pro in their current forms. In the meantime, HEC has been adding capabilities for dealing with spatial data directly in their models. This is an example of embedded approach where GIS capabilities are built directly within H&H model. If most of your work is in the HEC modeling world and all spatial processing you need is covered by their capabilities, this is great. You have one place where everything can be done. But if you want to use broader GIS capabilities, both for pre and post processing, then you are limited by the offering and can not easily integrate their process into broader data processing and analysis strategy. If you have a separate GIS group that does GIS and you have a separate modeling group, then that's easier. But if you're a person who does both, then that gets a little bit tighter. Let's now look at what we can do in Pro to support HEC, HMS, and RAS. We'll start with HMS. We talked about this workflow in the last webinar, so let me just summarize it here. The workflow is simple. We start with the DEM. We develop landscape tessellation using regular ArcHydro tools for terrain pre-processing and watershed and sub-watershed delineation. And then we create nodeling schema. The next step deals with sub-watershed and ridge characterization. These are all standard ArcHydro tools. And you can easily add any other steps for your particular spatial analysis by just building some geoprocessing scripts. And the final step, and the only HMS specific tool, is export of GIS structures into HMS basin file. That creates a standard HMS basin file, which is just a well-structured ASCII file. And then you can import that directly into your HMS project. This is an example of loose coupling where GIS and model communicate through data files. There is only one specific HMS tool. All the rest are standard ArcHydro functions that can be used to develop data for other node-link hydrologic models. And the whole workflow is geoprocessing compliant, so you can include it into your automation processes. You have full access to all capabilities of both systems, but the price you pay is that now you have to know both systems to be able to effectively use them. What can we do for HEC RAS in ArcHydro for Pro? On the pre-processing side, the geodatabase to SDF function creates a RAS SDF formatted file. Inputs to the function are feature classes with standard GeoRAS data structures. The SDF file can then be imported into RAS geometry model using RAS interface. As far as post-processing goes, once the RAS model is finalized and the results are stored in the SDF file, the post-processing is simple. First, run SDF to geodatabase function to create geodatabase with RAS spatial elements. This is the same geodatabase structure as produced by GeoRAS, including the cross-section feature class with water surface elevation fields containing the run results. The next step is to run the flood from cross-section H tool to create floodplain artifacts. This includes floodplain polygon, depth, and water surface elevation rasters. These are the same outputs that were generated in GeoRAS. So if you have your workflows that worked on results from GeoRAS in ArcMap, they will directly work on the results generated in Pro. This is also loosely coupled interface. There are two specific RAS tools for reading and writing SDF files. All the rest are standard archival functions that can be used to develop data for other hydraulic models. And the whole workflow is geoprocessing compliant, so you can include that in your automation. We'll be adding a few more functions on pre-processing to calculate cross-section and reach characteristics, and on post-processing to facilitate unsteady flow result ingest and floodplain delineation. Before I hand over the reins to Pete and Warren, let's do the final poll of the day. Mariah?
All right, we're going to go ahead and launch our first poll. Is integrated hydrologic and hydraulic modeling important for your work? We have a lot of people on the webinar, Dan, that are saying yes, it's important for their work. I'm going to let this run a couple more seconds. Yeah, most people attending today, Dan, said that this is important for their work. We've got some more responses quickly coming in, so I'm going to let this run just a few seconds longer. If you haven't already, please take the poll. All right, and I'm going to go ahead and close out this poll. And about 86% of our attendees today said yes, it's important for their work. And we'll go ahead with our next polling question. Are you familiar with ICPR4? Yes, I've used it. Yes, I've heard about it. No, I'm not familiar with ICPR4. So we have a large percent of our audience today that is not familiar with ICPR4. I'm gonna let this poll run a couple more seconds. About 30% say they've used it. And then I'll let this go just a few more seconds. All right, and I'm going to go ahead and close out this poll. 70% of our audience said, no, I'm not familiar with ICPR4, while 22% say they've used it. 8% has heard about it. And we'll go ahead and launch our final polling question. Do you use real-time flow forecasting? Yes, no. I know about flow forecasting, but I haven't used it. All right, so far from our responses, most people know about flow forecasting, but they haven't actually used it. We have about less than 20% that says yes, they've used it. And we'll give this a couple more seconds for last minute responses. All right, I'm going to go ahead and close out this poll. So about 11% of our audience today, Dan, said yes, they're using real-time flow forecasting. 46% said no, and 43% said they know about flow forecasting, but they haven't used it. And we're going to go ahead and make Pete a presenter, and he's going to take over.
All right, can you see it and can you hear me okay?
Yep, we can see your screen and we hear you fine.
All right, thank you. And thank you everybody for attending this webinar. Thank you, Dan, for inviting myself and Warren. And I'm going to talk about some of the structure of ICPR4, and then when I'm done, Warren is going to take over and show you how we integrate or interface with ArcHydro. So ICPR is interconnected channel and pond routing. It's been around a long time, probably since the early 80s, but it's mostly been in the state of Florida and then along coastal areas, and it's working its way now inland. It's much more now than just a channel and pond routing modeling system, as I'll show you. But one of the things that we work closely with Dan on is how do we share data between ArcHydro and ICPR? How do we move data around? There are some things that are much easier to do in GIS, and then there are other things that are easier to do over at the model end. And so that's some of what we'll be talking about. Let's see. So ICPR is actually now, ICPR4 is the 4th generation of the software, and it's evolved into an integrated flood modeling framework. And so we take a lot of different spatial data, and that spatial data is used to develop a surface portion of the model, and then other geospatial data is used for the groundwater modeling. And then other data is used for the unsaturated soil zone between the surface and groundwater. And that's mostly how we're communicating between the surface and the groundwater is through that unsaturated zone. We use various types of data to force the model: rainfall, ET type data, boundary conditions, a coastal surge. And then we have an adaptive time stepping algorithm where we can vary the time step not only temporally but spatially. And all of that goes into this integrated model. And from there, we can develop dynamic flood maps. So going to the basics of the model, we work with the 3 building blocks: are nodes, links, and basins. A node is just a location somewhere in the drainage system. Links are used to connect nodes together, and then basins are used for runoff computations. So we take the runoff from the basin, we assign it to a node, we calculate stages or water surface elevations at the nodes, and then based on those water surface elevations, we calculate flows through the links based on the properties of the links. In the 2D overland flow portion of the model, we can kind of extend that same basin node link concept. We work off of an unstructured triangular computational mesh, and then we develop these irregular shaped polygons around the vertices of the triangles. So you might think of that irregular polygon as a basin. The triangle vertices are the nodes, and then the sides of the triangles are the links. This allows us to fully integrate the 1D portion of the model with the 2D portion of the model. We do not couple them, we fully integrate those. Then we take those irregular shaped polygons, which we affectionately refer to as the honeycomb, intersect those with thematic polygon map layers such as land use and soils. We get a breakdown of the subpolygons, and then for each subpolygon we have soil attributes, land use attributes, and we can break it up into rainfall zones as well. So it's a truly distributed model. The way we develop the computational mesh is we use graphical elements, and we have 3 categories of these graphical elements. We have some that are used for terrain characterization, some that interface with the 1D elements, and then some of those are used for boundary conditions. And we can take a look at just a few of these. If we want to model flow between buildings, for example, we can add polygons that represent the buildings, and we refer to those as extrusions. We can put in something called a 1D/2D node interface point, which is an interface between the 2D computational mesh and the 1D drainage structure. So for example, in a roadway, if you have a curb inlet, you could place a 1D, 2D node interface at that location and then literally model the hydraulics of the inlet. And then that might drop into a catch basin with a closed manhole cover on the top. For those, we just use regular 1D node types. We can put in 1D channel links with surveyed cross sections, pipe links. We can refine the mesh by using break lines and breakpoints. And so from all of those graphical elements, we build the triangular mesh. And then from the triangular mesh, we derive the honeycomb mesh. And so the process here is you develop the graphical elements, adding detail where you want to refine the computational mesh. From those graphical elements, we build a triangular mesh. Then the honeycomb mesh is derived from that. And then we intersect the honeycomb with soil zones, impervious zones, rainfall zones. We form a set of subpolygons, and then we have the various attributes for the subpolygons. Also from the triangular mesh, we develop a diamond mesh, which is along the triangle edges. And between the triangular mesh and the diamond mesh, we intersect that with a roughness zone map and with DEM. And from there, we get the edge properties, and that's length, slope, roughness, characteristics, things like that. And then what we get out of all this, and I'm just going to show an animation of flood depths greater than 3 inches. And this is for that same system I just showed. We can pause the animation and right click and build a DEM from that and use that for whatever we'd like to use it for. So we have just a tremendous amount of other data that we can extract from the model. One other area that we've recently got into with ICPR4 is real-time flood forecasting. And we use the National Water Model forcing data to basically drive our model. So imagine building a 1D/2D model, overlay a map of the National Water Model 1 kilometer grids, and we have a system set up to automatically download the data, the gridded data from the National Water Model server. We take that data, reduce it into rainfall and evapotranspiration, and then that gets superimposed with the model, with the computational mesh and drainage networks. With the National Water Model, there's near real-time data. There are short-range forecasts, and there's an 18-hour forecast issued every hour. And then there's a medium-range forecast that projects out 10 days in 1-hour increments, and that's issued every 6 hours. So imagine that we have our model set up, we run a base model with the real-time data, and that just keeps running. Every hour we get a chunk of data in, we run the model for an hour. The next hour comes, we run the model for an hour. The base model is used to establish initial conditions for any forecast that we want to generate. So we keep track of groundwater levels, surface water levels, soil moisture conditions, and things like that. When a forecast comes in, we then spawn it off the base model. We're using the base model for the initial conditions, and then we project out based on the forecast data. And this is an example that we're working on right now. Warren's going to show you more on this in just a minute or two. But this is a kind of a closed system. Everything drains down into a hole here, basically a set of ponds, and then it's pumped out of there. And so the concern here is what happens if we can project a flooding condition 2 or 3 days ahead of time. Could we turn that pump on earlier before the storm arrives and create more storage in the system? So we took this, we used the National Water Model data for Hurricane Irma, we compared it to observed data, and then we did a forecast 4 days out, 3 days out, 2 days out, and then 1 day out. 4 days out, we weren't picking up a signal, but 3 days before the storm came, we were, based on the National Water Model forcing data, we could anticipate a problem 3 days out ahead of time. And then it was backed up by the 2-day forecast and the 1 day. So with that information, there might have been enough time to lower the levels in that pond system and create more storage. They didn't know that, and there was a lot of flooding in that area during Hurricane Irma in 2017. So now I'd like to turn it over to Warren, and Warren is going to show you how ICPR and ArcHydro interact with one another.
All right, thanks, Pete. All right, can you see my screen real quick before I start talking?
Yes.
All right, so I'm gonna quickly go over how we develop models in ArcGIS and transfer the data to ICPR4. And just to start with, usually when we're developing models for ICPR4 and ArcGIS, we start with what we call a GWIS geodatabase. And this is the Southwest Florida Water Management District's implementation of ArcHydro. It includes, basically, you could create a model from scratch in this geodatabase without touching the model at all, and have all the input data set up and take the information from the geodatabase, bring it to the model, and run the model. I typically don't like that approach because there's some stuff that you can do really easily in ArcGIS, and there's some stuff that you can really do much faster in the model. So my basic approach is I will go in and I will place all of my model elements for my nodes and my links, maybe the study area as well, and not populate any of the actual data for, say, your pipes or your storage in your nodes or your initial stages. Just get everything placed geospatially and get the overall network laid out. And once that's done, we've developed these tools in ArcGIS Toolbox. They're just simple Python scripts where we can take this information and write it out to CSVs, because this is a loose coupling with ICPR4, and then we can take that CSV information and load it into our model. So the first step, after I create the layout, I will go to the GWIS 2.1 to the ICPR4 tool. And the tool works is fairly simple. You select the geodatabase that you want to export. You specify a file stem. This is a prefix that goes in front of each of the files that are written out as part of the export. And it's just an identifier, and there'll always be an underscore added after the file stem. And then you just go in and you specify the folder that you want to export the information. And you have the option to export specific features. 99.9% of the time you're going to export them all. This is more along the line for do error checking, because sometimes the geodatabase is set up incorrectly, and the data won't export for some of the items in the geodatabase, and this is how you can narrow it down. We're going to skip running this because this tool takes a few minutes just for the sake of time. But you click OK, and then if you go into the folder where the data is written out, you'll see a series of CSV files as well as a shape file, this which represents your basins. This gets written regardless if you have basins or not. This particular model doesn't have 1D basins. It's an integrated surface water groundwater model that uses the 2D. Honeycombs that Pete was talking about before, but you'll get it regardless. And then you can take this information once it's exported and then go into ICPR4, which is right here. And the network's already been imported into the model, but I'm going to show you real quick how it works, because the import into the model using the CSVs is actually fairly quick. To do that, we just go import GWiz. We specify the folder where we want to import the information. We specify the file prefix. And if you have a basin information you want to import, you can specify that. We do not. I'll get a bunch of messages saying I don't have it. So I'm just going to close this. Say yes, I don't have a basin map layer. Basin map layer not included, and click OK. And then I have my model network. And what just happened, you kind of don't see it, but behind the scenes, everything that was in the model just got cleared out and replaced with what was in the geodatabase. And if I were to go in and look at the actual model data, you can see that none of the initial stages are specified. The storage for the nodes that need storage isn't populated. Also, none of the link information for your pipes or channels, all that is empty, because usually I like to input this data in the model because it's a lot faster, in my opinion. Although there are hydro tools to generate your stage area, which I use sometimes to populate the node storage, but most of the time I like to work in the model because it seems to work a little bit faster. And once you go in and input all the data, you'll end up with a final model, which has all the model information, which is what we see right here. A lot of these features have to do with the surface and the groundwater that Pete was talking about before. It's just more user-friendly and more time-effective to create that information in the model. All the pipe information is populated in this model, as well as the node initial stages and nodes that have storage is already populated. And this model actually runs. So at this point, when you get it completed, you usually want to have your model data match, or the file geodatabase, the GWiz geodatabase, to match what's in the model. Mainly because if you're distributing this to someone, not everyone has ArcGIS, not everyone has ISPR4, so you have to be able to provide them the information in a format that they're able to read. And by using these tools and able to go from the model back to the geodatabase, you can guarantee they match. So to export the information from the model, it works with CSVs as well. You just go to File, Export, GWiz, specify the output folder, specify the file stem, which is OR, specify the scenario, and we're going to use ECNWM, and we don't have a basin map layer, so I'm going to click OK. It's just letting me know I don't have a basin map layer, which is fine. This takes a few seconds to run, depending on the size of the project and the complexity of the features and the geometry. It can take a little while to run. But once it's complete, if I go to the geodata or go to the folder where the information was output, I have all the CSVs. Not all these CSVs have data. Some of them are empty. It doesn't really matter for the migration back into the geodatabase, because I can go back to the tool, and we have an ISPR4 to GWiz 2.1 tool, where you go in, you just specify the folder where the CSVs are located at, specify this file stem, and then specify the geodatabase where you want to write out the data. And this is actually a different geodatabase than the one that I'm displaying right here, mainly because I just want to show you how the tool works. But realistically, what would happen, you'd import it into the same geodatabase, and the tool goes through and looks at all the information and updates, removes or deletes, and adds information as necessary. And this tool takes a little while to run, especially for this project. We have some fairly large data tables in the file, so I'm gonna skip running it. But the one thing I want to kind of end with, I know I went through that really quickly, is once you have all the information in the geodatabase, you can do some really cool things. And like Pete was talking about with forecasting, you can set up hyperlinks based on the final data set, and this matches the model completely. It's a exact duplicate. If you set up hyperlinks, and I set them up for these nodes, if I select one of the nodes, actually it's 1570, I have a hyperlink for our live forecasting. And I can actually pull up the model results. And Pete, do you want to say anything about this graph?
Just real quickly, this model is running live right now using the National Water Model forcing data. And the blue part of the graph is based on the real-time forcing data, and that takes it up to within about an hour or so where we're at. And the red is the last medium range forecast, and that forecast out 10 days. And so you can see a kind of a blue blip there. We had a pretty good storm come through about a week ago, and it's picking that up. And then it's forecasting about a week from now another storm event. Now that forecast might change. We've elected, even though there are 4 medium range forecasts per day, we're just running one of those per day, which we think is probably adequate. So so right now there's a blip between the 21st and 22nd of April, and we'll probably have another forecast run this afternoon to see if that changes, and those often do change as we get closer to a particular event.
All right, and I'm going to turn it back over to Dan.
And you see my screen?
Yes.
Yes.
All right. And thank you. Thank you, Pete. Thanks, Warren. And before we wrap up today's webinar in the series, here are a few thoughts. So model integration is an active area of ArcHydro development. So we are adding additional tools for H&H modeling, and we will also be bringing the ICPR4 tools into the Pro environment. So please get involved with ArcHydro, download the tools, take them for a spin, let us know how it goes. Let us know what works well, what can we do in the future, and use our community pages for water resources, which is home for ArcHydro, or email our team directly. And when you communicate with us, the more focused you are in your comments and questions, the better. All right, so let's take some question. Mariah, do we have something?
Yes, we got quite a few questions. We'll start. Jennifer asked, she said that they have ICPR4. How do they download the ArcHydro toolbox?
Yeah, Warren, do you want to get that?
Yep.
Is it relation to the ArcHydro toolbox or the ICPR4 toolbox in ArcGIS? If it's ArcHydro, Dan can answer that.
It just says the Arc toolbox.
I would assume, Warren, that it would be the ICPR toolbox in ArcHydro.
In ICPR4, if you go to File, Check for Updates, it'll direct you to the download and the install exe for all the Python scripts that go along with that toolbox.
All right, and then our next question is regarding ICPR4, are multiple day storms able to be modeled?
Yes. There are a couple of ways to do that. One is to build your own rainfall distribution, where you stack the storms up back to back. Another way to do it is to run one storm and then put in a delay in your basin data. We have a time lag, and so you can set up 2 identical basins. First one, you run the first storm through. The second one, you may put a delay in there of 24 hours or 48 hours, and then run the second basin through, and then both of those will be combined at the node. So there are several ways. Warren, do we have something in our help system on that? I think we added some stuff for that.
I believe we do.
And we can share that resource with attendees as well, Warren and Pete, so we can get that to them.
Mm-hmm.
Okay.
And then another question regarding ICPR4. One of our attendees is asking, does the program have any limitation in accuracy dependent on the size of the project? For example, 1 acre site versus an 1,000 acre site?
No, there really isn't. We can do, you know, flooding of your swimming pool in your backyard if you want. And we have some people working with models that are like 30,000 square miles, you know, massive size. And both can be accurate, but it depends on how you put the data together. There are some papers that have been published on scaling with ICPR.
And does ICPR work in ArcGIS Pro?
Dan, you had, we developed it in ArcMap. The tools are working in ArcMap, but I think Dan took those and pulled them into ArcPro, right?
So the specific ICPR 4 tools are not in Pro yet. This is something that will be working with Pete and Warren as soon as this webinar is over, and so we'll be bringing this into the Pro environment. But probably it's going to be close to a couple of months before it's there.
Okay. One of our attendees asked when they would want to use ICPR and not the SWIM. Is there a specific situation when it's advantageous?
Well, I am a little biased, but but what I can say is what ICPR and SWIM are similar in many respects for the 1D modeling. The EPA open source version of SWIM does not include 2D overland flow. Now, there have been some other vendors that have tacked on 2D overland flow with SWIM as the 1D component. But the other area where ICPR addresses that SWIM doesn't is integration with 2D groundwater. So if you have systems that need both surface and groundwater, then ICPR has a fully integrated groundwater package and works between the superficial aquifer system and the surface water bodies.
All right, thanks, Pete. And that's all the time we have for questions. Dan, I'll pass it back to you.
Oh, thank you. So let me do a couple of closing remarks. Let's see. All right. So over the last 4 webinars, we got many questions and comments, some quite detailed that we could not really be able to answer in the current 1000 attendee format. So we decided to try something new. We call it ArcHydro office hours. Think of your college days when you would walk into the professor's office and ask whatever in a more intimate setting. We'll set a 1-hour session once a month, do a short demo, maybe 10 minutes or so, and then open it up for discussions. It can be about a specific topic or something more general on ArcHydro or in general water resources and GIS integration. So this will be limited to a smaller group, 20 or so people, and will be announced through our Esri meetup, through which you will be able to register for the event. And we'll have some more details through a blog post in the community page. And the first office hour is already scheduled for May 11th, and we'll focus on terrain pre-processing and watershed delineation. And a reminder that all 4 webinars in this series are available on demand in case you missed some or want to point your colleagues and share the wealth. And with that, I want to first thank you, our presenters, and Pete and Warren today, and Dana, Annalise, and Gina last webinar. And special thanks to Krista, Mariah, and Christine for pulling the strings behind the scenes. Without them, this series would not be possible. And to all our participants, wherever in the world you are, well, thank you for sharing the time with us. Doing these webinars is fun. Doing it for 1,000 people is 1,000 times more fun. So thanks again, and I hope to see you and hear from you soon. And until then, stay safe and goodbye.
Thanks, everyone.
Bye.